right, we're going to do a video here where we do a whole bunch of different integrals. And we have to figure out what technique works best. So let's take a look at this first one. Integral of 11 over 4x dx. Sometimes it's best not to overthink these. So what I can do here is I can rewrite to make this a little bit clearer. The 11's a constant, and the 4, which is really like 1/4, right? That's also a constant. So hopefully we'd all agree that I can pull out 11/4 and then get integral of 1 over x dx, right? If I multiply 11/4 times 1 over x, this is exactly what I get. And the constant of 11/4 can be pulled out, and now it should be bread and butter time, right? Do you know a function whose derivative is 1 over x? And the answer to that is yes, you do. It's ln absolute value of x, and of course, when it's an indefinite integral, we have plus c. So don't forget what you found here. You found a family of functions differing by a constant such that if you took the derivative of this family, you would get 11 over 4x, all right? Hopefully you weren't thinking power rule with 1 over x, right? So maybe someone was like, well, why couldn't I just write this as x to the -1 and then do the power rule, which is add 1 to the power and divide by the new power, right? Well, if you did that, you'd get this, and that doesn't work. In fact, the power rule does not apply when n equals -1, right? So the power rule for x to the n does not apply when n equals -1. So this one, you just had to recognize it, right? All right, no big deal. Let's move on to the second one. All right, very similar problem, but a different approach. So I'm still going to do the same thing where I'm going to pull out the 9/5, right? Because those are just constants. And I'm going to get 1 over x to the 8th. So it actually turns out that this is not ln. In fact, it's only ln when it's 1 over x. And so what you want to do here is actually rewrite this as x to the -8 so that you can use the power rule, right? So power rule says add 1 to the new power. If I add 1 to -8, I get -7. And then multiply by 1 over that new power, all right? And then don't forget that I have my 9/5 out here. And then again, plus c, right? I can spruce this up. So I'm going to get 9 over 35. In fact, it's going to be -9 over 35, x to the -7 plus c. That's a totally fine answer. Maybe if it's a multiple choice, maybe they go ahead and use that property of negative exponents. They chuck that x to the -7 in the basement, rewrite the exponent as positive. That is also a good answer. Obviously, if it's free response, you can leave it here. If it's multiple choice, you might have to find that. Again, don't lose sight of what you're finding. A family function such that if you took the derivative of this, you would actually get 9 over 5x to the 8th. If you don't believe me, go ahead and check it out. All right, take a look at this one. So, we still got terms with like x to powers in it, right? So we can consider this like some sort of an exponent example. Hopefully you right away, you're like, okay, that -6, I'm going to pull that out. That's not going to affect anything. And then the question is, what do you do with this? Maybe you think use substitution, but use substitution is not going to work here. In fact, it's easier than that. This is just a straight up recognition, right? So one of the first things you try when you do an integral problem is to recognize it. In other words, I ask myself, do I know a function whose derivative is 1 over 1 plus x squared, right? Do I know that antiderivative? And hopefully you say, yeah, I do. That's actually arctangent of x. So I'm going to get -6 and then arctangent of x, and then, of course, plus c. So again, family of functions differing by a constant such that if I took the derivative of this, right, I would just get -6 over 1 plus x squared, right? Remember the derivative, just a little reminder, not that I really need to write this, but the derivative of arctan of x is just 1 over 1 plus x squared, right? That's the idea. And then the last one we'll do in this short little video is going to be question 4. So this one's a little bit of a doozy here. So a couple things I'm going to want to do with this guy. Like just like in all the other problems, we'll pull that 7 out, and then we get this. And then I'm going to rewrite this now using negative exponents. So it'll be the integral of 3 to the -x dx. And so now this is not a situation where you use the power rule. Now you might be saying, why not? Why can't I use a power rule? Well, because it's not a power function, right? So a power function is going to look something like x to a number, x to an n. All right, this is an exponential function. So this is an exponential function where you have like n to the x, or maybe I'll say a to the x, where your number, your base is going to be 3 or 4 or 5 or whatever, but the variable is in the exponent, hence the name exponential function. Now, problem probably would have been a lot easier if it was e to the x, right? Because we all know that the derivative with respect to x of e to the x is simply going to be just e to the x. And so then, therefore, the integral of e to the x dx, we all know, is just going to be e to the x and then plus some constant, right? I'll take it a step further. And if you remember, the derivative with respect to x of e to the, say, stuff, we'll just say ax in this case, would be e to stuff times the derivative of stuff, right? So that's how you would take the derivative of e to the ax, right? That's just a chain rule. So then if I integrated a e to the ax, right, then it would just be e to the ax and then plus c. But sometimes this a is not here, right? So what could we do? Well, we can kind of pull this a out and divide both sides by it. And so we would get this rule for when we integrate e to the ax, right? And we've kind of done this when we were doing integration by parts, right? Do you know a function whose derivative is e to stuff? Yeah, it's e to stuff times 1 over the derivative of stuff, right? That's like that shortcut chain rule, but it's not really a chain rule because it only works for linear u substitutions, right? So that's kind of what will be going on here. So again, all this is just for e, and you're like, you don't have e here, you have 3. Well, did that just to maybe set your mind up a little bit. So what if it was the derivative with respect to x of a to the x? Does anyone remember what that derivative rule was? Well, hopefully you do. All right. It is simply going to be a to the x, but then it's ln a. So the only difference is you multiply by the ln of the base, which technically you do here too, right? But the ln of the base would be the ln of e, and that's just 1. Okay, so when the base is something other than e, the derivative of a to the x is a to the x ln a. So you're like, all right, so if I'm going to now integrate this, I'm going to kind of skip a couple of steps here just to get to the big dance. If I'm going to integrate a to the x, right, dx without the ln a, all right, what would it be? Well, it's going to be 1 over ln a times a to the x plus c. So it's very similar to the derivative rules. Instead of multiplying by ln of a, you multiply by 1 over ln of a. And you kind of do something similar to what I did here for you to derive that. So that's kind of important. All right, so now couple that with this isn't just a to the x, this is a to stuff, but stuff happens to be linear. So there's going to be a whole bunch of things we can do here. All right, so you have the constant 7, no big deal. A function whose derivative is 3 to stuff is going to be 1 over ln of that base, 3 to stuff, and times the derivative of 1 over the derivative of stuff, right? So that's that reverse linear u shortcut rule being applied. This right here is just basically my understanding of a function whose derivative is 3 to the negative x. And so when I clean all of this up, I'm going to get negative 7 over ln 3. Move this little screen here if I can. And then 3 to the negative x. And then, of course, plus c. I should probably put the plus c there. And that's my final answer. And again, if you don't buy that, just take the derivative of this, right? So there's a family of functions differing by constant, such that if you took the derivative of this, you would literally just get 7, 3 to the negative x, which is equivalent to 7 over 3 to the x. So I did that one kind of fast, but if you play the video back a bunch of times, maybe even do the check here, take the derivative of this, I think you will get it. If I were you, you might want to put this guy in a happy cloud, and you can have this as a integration rule just to remember. All right, be good.